which is you can actually explicitly say what the eigenvectors of a hypercube are. And the hypercube is a very nice structure. And you probably know that already. And I'll just point this out so you can try this at home. So if you start with a hypercube, and the question is, we often think of the structure, but how do you think of the vertices? And there's a couple ways you can think about them. So let's do. I'll be dangerous here and try to do the Q3, three-dimensional hypercube. So one way to think about the three-dimensional hypercube is just to think of strings. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, and 1, 1, 0. And then just say any two vertices are adjacent if and only if the strings differ in exactly one entry. But there's another way. Once you have the strings, you can actually think of it, and it doesn't take very long. You're like, oh yeah, of course, it's the same thing, Steve, but I need bigger circles to draw. Which is to say, well, now what you can do is you can make the vertices subsets. And specifically, if I'm doing the 3 cube, I'm going to do subsets of 1, 2, 3. So you have your empty set, you have, I'll call this 1. Maybe I already regret using set notation, 2, 1, 2. And out here, this will be 1, 2, 3, this 3, well, 1 and 3, and that's very hard to read. This is just 3, and this is 2, 3. And then you say, well, 2 are adjacent if only if they differ in one element. And it's easy to go back and forth. You can say, oh, okay, well, this just says, okay, you have your element 1, element 2, element 3. And then you can say, okay, there's my set. And now, I said eigenvectors. So, it turns out, well, there's 2 to the n vertices. So that means there's 2 to the n eigenvalues. So there's also 2 to the n eigenvectors. And what you do is you say, well, gosh, wouldn't it be cool if we can think of the vertices as subsets of 1 through n? What if I can associate eigenvectors with subsets of 1 through n? And you can. And here's the way you do it. So for each t, a subset of 1 up to n, you make an eigenvector. And the way you do eigenvectors, if you thinking about graphs, is you say, well, the way we think of eigenvectors is we think about assignments to values on vertices. So I just have to say what's happening on each vertex. So each vertex is associated with a set, S. And so the key here is that for each vertex, which again I think of as a set, S, then assign the value -1 to the intersection of S intersect T. And so all the eigenvectors can become plus minus 1 vectors. Now there's a couple of eigenvectors which are really easy. What if T is the empty set? What eigenvector does this produce? What are the entries look like?
Well, S intersect T would be empty.
S intersect T is always empty, yes, because you're intersecting with the empty set.
So it's the all ones vector.
It's the all ones vector. And cubes are regular. And so this leads to your all ones. And the eigenvalue turns out to be, well, it's n, because we're thinking of n-dimensional cube. What if T is everything? Then what does the eigenvalue look like? Or is there a nice way to describe it?
It's 1 if S has an even number of elements and it's odd otherwise.
Right. Yeah, it's like you split your vertices into 2 parts. And it turns out that what happens is, hypercubes are bipartite graphs, and so you can split your vertices into, even number of elements, an odd number of elements, and then we just say, oh, hey, the only way you can form an edge is you have to differ in one element, so all the edges go in between. And then what this particular eigenvector does is it's all ones on one side, all minus ones on the other side, and so it's very nice. And this corresponds to the eigenvalue. Anyone able to do this quickly in their head? Negative n, because each vertex is adjacent to n other vertices. And so if I take something here, I have n neighbors that are minus 1, so the sum is n times minus 1, just minus n. And, well, we can try something a little bit more interesting here. We can actually go with this one. So not the empty set, not everything. What's something in between that we can try with our 3 cube?
I mean, just take any set containing 1 and 2.
Yeah, we can take any set. So someone has suggested the set 1, 2. All right, so if that's our set, let's find out what our eigenvector looks like. And we'll see what the eigenvalue is. And it does turn out, by the way, that there is a nice way to describe the eigenvalue in terms of the size of T. Okay, so the set 1, 2. So starting in the corner, how much does 1, 2 intersect the empty set?
It's just the empty set.
Yeah, it doesn't intersect very much. It's hard to intersect the empty set. And so, negative 1 to that says plus 1. Okay, how much does 1, 2 intersect with 2? 1 time. Minus 1. How about with 1? Minus 1. How about with 1, 2? Plus 1, right? Because it intersects twice. Now this way, this just seems like the thing you were talking about where it's what was going on before. But hold on. Okay, how many times do we intersect with 3? None. So that's a 1. That should be a 1, 3. It's hard to read my bad handwriting. So that's a negative 1. 1, 2, 3. Positive 1. 2, 3. 1. So it's a negative 1.
So it's just, like the front face that you've drawn there, it's just taken an eigenvector for that graph and duplicated it, sort of, or
kind of, in some sense, yes. Now, can you see what the eigenvalue is for this particular one? Hint, just pick a 1 and add the neighbors. Minus 1, right? Because no matter which neighbor you pick, which just has all 1s, the sum of the neighbors is minus 1. And if you pick a minus 1, well, the sum of the neighbors will all be plus 1, which is consistent because you want minus 1 times minus 1. And so this has eigenvalue of minus 1. And in particular, there's a way to figure out. I think it turns out to be something like n minus 2 times the order of t is what the eigenvalue is. And mostly you say, well, look, either I look at my neighbors and I say, how many times can I change sign and how many signs can I not change sign? Okay, so if I fix a vertex, how could it be that I don't change my sign? What would I need to do? Now remember, moving from vertex to vertex is you either add an element or take out an element. So if nothing changed, what does that correspond with? Well, if nothing changed, then we want to do something outside of the intersection so that the size of the intersection doesn't vary. And so you say, okay, if nothing changed, well, then we have n minus the size of t things that we could play with. So that says you have n minus size of t plus 1s, if you like. Now if we change, how many ways can we change? Size of t. Because you can either add or remove any element in t. So you have size of t things which will have different signs. So you have n minus size of t with the same, size of t with different, and so lo and behold, you have to ponder about this for a minute, but hopefully not too much more than a minute. The eigenvalue turns out to be n minus 2 times the size of t. And you can even show that these are all orthogonal with each other, and we'll skip that. But there is a fun thing to point out. That says that hypercubes have really, really nice eigenvectors. And so this leads into the sort of belief that hypercubes are nice, and they've been extensively studied. There's lots of reasons why people care about hypercubes. If you're a computer scientist, for example, you care about hypercubes because you think of the hypercubes are strings of all possible 0-1 strings. And so it's all possible 0-1 states if you have n registers. And then you're just trying to understand, well, how do you understand things if you can perturb things slightly? And so there's something which we'll mention later in the semester, not today, called the sensitivity conjecture, which relates about hypercubes and how sensitive 0-1 functions are. And then it was a conjecture for 50 or 60 years. And then it was proved a couple years ago in a paragraph using spectral graph theory. And people are like, wow, spectral graph theory, finally, you're doing something. But all of us in spectral graph theory were like, yeah, we just knew it was a matter of time. People would recognize us for how cool we were. The other thing that you can do is if you stick all the plus minus 1 eigenvectors into a matrix, I'll just point this out, what you get, and I'll do it for, not for C8, sorry, not for the 3 cube, but the 2 cube. You get something that looks like 1, 1, 1 minus 1, minus 1, 1 minus 1, 1 minus 1, and something that looks like that. And this is an example of a Hadamard matrix. And this is, again, another structure that's been extensively studied and people care a lot about. And, well, it turns out that the simplest Hadamard matrix corresponds with eigenvectors of the cube. Are there others? Well, yes. Because, for example, the cube only happens to exist when you're a power of 2. But Hadamard matrices are believed, this is a conjecture, it's the big conjecture in Hadamard matrix theory, to exist for any multiple of 4. So, and one of my recent papers, which I thought was pretty fun, because I'm somebody who likes computation, and we said, all right, what are all the possible graphs, not just the hypercube, but all the possible graphs where you can get your eigenvectors are plus minus 1. And we have the answer up through 36 vertices. And not as easy as you think. I wrote a program that was not bad. It would only take a couple years to run for 32. 36 you can knock out with a theorem that takes half a page. It's actually, maybe I'll show it to you by the end of the semester. It's a really cool proof. It's one of those book proofs where it's like, I can fit the whole theorem on a slide. But for 32, it's like, okay, I have a program. It'll take a couple years, but we'll have an answer at the end. And then I knocked on my wall. And if you're not familiar with my office, my wall is shared with Bernard Leditsky. And Bernard said, all right, give me your code. So he took my code, rewrote it in C, didn't change anything about the algorithm. I mean, it was like the easiest job for him. I had a great algorithm. It's just, I didn't know C. And then he borrowed a small supercomputer over in the Czech Republic and ran it, and then he had an answer like 2 days later. And so the key is write your programs in C and know where some spare supercomputers are laying around that you can borrow, and you can solve hard problems. So, all right, anyways, that was a big digression. Sorry about that. But, well, we should talk about hypercubes. There's probably whole books written about hypercubes, and if not, someday there will be, because there's a lot that can be said. All right, I do have a goal for today, and I want to start something. So I want to go back to our Build a Matrix workshop. And when we talked about this at the start of the semester, where we were saying, well, where we're at is that we have a graph, and we want to build a matrix for the graph that we can do something with. Now, generally speaking, there are 3 things you build off of. Now, there are, of course, many things that are possible, but when it comes to understanding how graphs are connected, there are 3 main categories. So one category that you build off of is the adjacency category. And in this category, you have your adjacency matrix, and just the most obvious thing, you have your Laplacian, and you have your signless Laplacian. Now you can do some various things. You can play around and do tricks. You can say, well, I'll take something halfway between the adjacency and the Laplacian. Or there's even ways to do, it's not quite a matrix. There's things called generalized characteristic polynomials, which are normally characteristic polynomials. You have one variable, x. But in generalized characteristic polynomials, you get 2 variables, x and y. And what they do is that you can take the following. You can look at, say, the determinant of, I'll call it xi minus yd minus a, something like this. So there's a couple of variations, but this is more or less what you can do. And this is a bivariate, 2 variables, and it captures the adjacency spectrum by, you just let y equal 0, captures the Laplacian spectrum if you let y be -1, captures the signless Laplacian if you let y equal +1, and then you can capture other things as well. And so there's big broad umbrellas that you can do. But more or less, okay, you've got your adjacency, you can fiddle with the diagonal with your degrees. That's the idea for this category. And that's one we've talked about, and we're pretty comfortable with. And when it comes to spectral graph theory, I would say this is one of the two major ones. The other major one, which is what we'll start now, is built on transitions. And really, you should think of this as random walks. Now, we can give it a couple different names. One name is the probability transition matrix. One name is normalized adjacency matrix. And another name is the normalized Laplacian matrix. And but essentially, for all intents and purposes, they're the same. And it's just a matter of just, what do you like? There are reasons to prefer one to the other. Because I went to graduate school at UC San Diego, of course, I must talk about the normalized Laplacian matrix, and that's what I'm known for. When it comes to spectral graph theory, I would say that I'm known for two things. One, I'm fixated with co-spectrographs. I just think they're fun. And two, I say a lot about the normalized Laplacian. And that's because my PhD advisor was a normalized Laplacian person. She wrote the book on the subject called Spectral Graph Theory, which, given the title, you would think would be fairly broad, but really it's mostly focused on the normalized Laplacian. And so this is what we're going to talk about for the next several classes. Now, do you remember what the third category was? And I would say that these two are the main ones. There was a third category. Think about what the goal is. So we want to say, how are things connected? So adjacency is like there's an edge connecting you or there's not. Transitions, we haven't been very specific about, but really you should think about transitions there's a process happening. Can you move from this state to that state? How likely is that to happen? So what's another way you can measure how connected two vertices are? Because ultimately, graph theory is about connections. I know it's been quite a while. This is way back in the far distance that we talked about these things.
Can you measure the distance between the vertices?
Yes, we can measure distance. Yes. Distance. And this gives you things like the distance matrix. But there's other matrices as well. They've done things like the distance Laplacian, distance signless Laplacian, normalized distance. But we will, when we get to this point, when we talk about the distance matrix properly, we'll say it just doesn't feel right from a matrix perspective. It feels wrong. But that's a discussion for that day, not for today. We'll talk about why it feels wrong later on. All right, so let's talk about our transition. So now we're transitioning into transitions. Whoa, that sounds very meta. Okay, so let's start by talking about random walks on graphs. And so you might have an underlying graph. We'll keep things simple for now. We'll do our PA graph. What does it mean to take a random walk? What's sort of the intuition?
The probability of moving to each neighbor, or set the probability of moving to each neighbor as 1 over the...
You're already being very sophisticated. It's like, okay, we're going to set a probability, we're moving, but sort of like, keep it simple for now. What does it mean to do a random walk? Don't worry about like details, just the idea.
You take some number of steps and it's possible to end up at any of the places that are that distance.
Well, you take some number of steps. Now, of course, you have to be careful on what does it mean to end up something at that distance. You start someplace, right? It's often how we think about it. You start somewhere, and then you just move to a neighbor. Which one? Random. Okay. Then you move again. Which one? Random. Just pick. And you're allowed to, if you move along, you're allowed to go right back. So there are things called non-backtracking random walks, which get more complicated. So we're going to just keep things simple for right now. And so we say, okay, so you start somewhere, and at each stage, you make a move. Now, we'll get into, as you were suggesting, the specifics. How do we choose where to move? And so the simplest choice is we just say, well, let's just treat all roads as being equally likely. 2 roads diverged in yellow wood, and I flipped a coin and took one. I think that's how the poem goes. So, and so that coin made all the difference. Okay, so we have that the probability of moving from state I to state J. So when I say state, you should think of that means just vertex. Vertex I to vertex J. Well, it's one of 2 things. So you suggested 1 over the degree. So currently we're at state I, so 1 over the degree of I. And when is it this? Yeah, if we can actually move. So if I is adjacent to J, and 0 if I is not adjacent to J, which is else. Yeah. So I can't jump from 1 to 4 in a single step, because there's no way to me to make that transition. It's not an option. So okay. So we can construct a matrix P, and I don't think we've used P before. So, and even if we have, well, we're going to use P again. So, so P, our probability transition matrix, and we've already defined it for all intents and purposes. It's this probability here, and so P I J again. It's 1 over the degree of I if I is adjacent to J and 0 else. Now, let's work through for this graph what it is. All right. So, carefully, we go through and we work through. So I'm going to label these so that there's hopefully not too much ambiguity. All right. If I'm in state 1, or if you like, I'm at vertex 1, what can I do? Move to 2, or I can move to 3. And then each one is 50-50. So we can write that as a 1/2. So I can move from 1 to 2, probably 1/2. Or 1 to 3 with probability 1/2, and I can't stay because there's not a loop, and I can't jump to 4 because there's not an edge. Okay, so how about for 2? What can I do? 1 or 3, each with probability 1/2. 1/2, 0, 1/2, 0. All right, what about 3? 1, 2, or 4, and then probability 1/3. So 1/3, 1/3, 0, 1/3. And if I'm at 4, what can I do? Go to 3. I have to. So that's probability 1. All right. What do you notice about this matrix? It's not symmetric. Ah, that's sad.
It has the all ones vector as an eigenvector.
Okay, so another observation. We have that 1, the all ones vector. Let's be careful here, because it's not symmetric. We can't just say eigenvector. What kind of eigenvector? Is a right eigenvector. So when you multiply on the right side, it works. But if you multiply on the left side, it may not work.
Which is because of the rows summing to 1.
Yeah, now why do the rows sum to 1? Why does that make sense?
You have you have 1 probability of moving somewhere.
Right. If you're out of state, you have to do something. So that's why everything has to sum to 1. So is the right eigenvector with eigenvalue 1. Cool. All right. Now let's, there's so many things we could say right now, but not so much space for us to say it in. Maybe I'll sneak over here and take some space. We've made a comment here that 1 is the right eigenvector with eigenvalue 1. What does that tell us about all the other eigenvalues?
Perpendicular.
Well, that's eigenvectors.
Oh, no, not the values. Okay.
Magnitude less than or equal to 1?
And why is that?
Rowan Frobenius?
Yeah. And how do we know that? It's non-negative. Yeah. Well, you need non-negative. That's the key thing. If you're non-negative and your largest eigenvalue in magnitude will be associated with an eigenvalue which has all positive entries. Well, it turns out that the all ones vector has all positive entries. So it has to be associated with the eigenvalue of largest size. So cool. So all eigenvalues have size at most 1. In fact, we can go further than that. Not only are all other eigenvalues have size at most 1, if we make an additional assumption, some additional assumptions about our graphs. Okay, so again, this goes back to Perron-Frobenius. Does anyone remember what our assumptions are to make things nice? Yes! Oh, you got the hard one right off the bat. Yeah, so there's sort of 2 important facts you need. So sometimes you'll hear people talk about ergodic, which is just a fancy way of saying mixing. So ergodic theory is the theory of mixing. And one thing you need is aperiodicity. It's a very long word, but you don't want it to have all your periods have a common divisor. Now, aperiodicity for us, if we're dealing with simple graphs, what does that turn into? Yeah, not bipartite. What's the other thing you need to have good mixing? So just think about if you want things to mix well. So in other words, in terms of a random walk, I want to be able to sort of like spread out evenly. Connected. Yeah. And the technical term you'll hear is irreducible.
Right.
And so it's the idea of being irreducible is you can't do block diagonal where you have a bunch of zeros down here. That's irreducible. But the nice thing about Perron-Frobenius, it's more broad than just symmetric matrices. They were like, I don't have to keep it real. That's how cool it is. Like, I can do it all. So if you have these 2 things, if you're connected and not bipartite, then you can actually say that all other eigenvalues, besides 1, are strictly less than 1 in magnitude. So that's a very useful thing, and we'll point out something that comes from that in just a second. Yes, we'll talk about stationary distribution. Very good. That's going to be important. And so we'll have to talk about that as well. It's not symmetric. I want to come back to this. So far this semester, we've been keeping with things which are symmetric. And what's nice about symmetric matrices?
Real.
Yeah, we get to keeping it real. Will the probability transition matrix have real eigenvalues? And why will they? Yes, good. Because the second part of the question is implying yes. And so one of the ways we'll get there is to sort of understand how can we think about this. If one were to take a look at the probability transition matrix and squint their eyes so hard that all they could see is like, I see where the zeros are and I see where the non-zeros are, it would look like what?
It just looks like an adjacency.
Yeah, it looks an awful lot like an adjacency. And then, so it's well, it's kind of like I took an adjacency and I did something. You scaled it in a very particular way. You scaled each row by the degree. Now, scaling rows means left multiply. And we didn't actually scale by the degree. I misspoke. We scaled by 1 over the degree. So how can you scale by 1 over the degree? By multiplying by something on the left. Something maybe diagonal.
D. The matrix D.
Well, almost D.
Almost.
It's D inverse. Right. And so we get that another way to think about the probability transition matrix is it's D inverse A. Now this alone does not make the graph have real eigenvalues. But I want to point out that we have this nice fact. Well, it doesn't have the same spectrum as A. Weird things happen. And we'll talk about some weird things that happen. And in particular, we've gone really committed to, as we've talked about things like adjacency and Laplacian and sinus Laplacian, it's like, it counts stuff. These matrices are good at counting. And we're basically going to come to the probability transition matrix and say, this doesn't count stuff. This is really bad at counting. But that's okay. We get some trade-offs. Now here's a quick observation. Now we're assuming no isolated vertices, because otherwise D inverse. Okay, what? Hopeless. Hopeless. What happens if we multiply by D to the 1/2 times P D to the minus 1/2? Well, that would be D to the 1/2, D minus 1A, D to the minus 1/2. Just D to the minus 1/2, A, D to the minus 1/2. Now, first off, a couple of things. What's true about our original matrix P versus D to the 1/2 P, D to the minus 1/2? Now don't try to think too hard. If it helps, how do these matrices on the end compare?
They're inverses.
They're inverses, so what do we have?
They're similar.
They're similar. So P and this matrix are similar. So P and D to the minus 1/2, A, D to the minus 1/2 are similar. They have the same eigenvalues. And by the way, I mentioned this matrix before by name, but I haven't said what it is. This is what you would call the normalized adjacency. Now, in this one, what can you say about this matrix? It's symmetric, because you can take the transpose. These are all symmetric matrices. So if you have take the transpose, you get d to the minus 1/2 transpose times A transpose times d to the minus 1/2 transpose, but then transpose do nothing. So this one has real eigenvalues by symmetry. So our conclusion is, oh, that means that our original matrix also has real eigenvalues.
Similar to A, but similar to something else. Symmetry.
Yes. And I will say d to the minus 1/2 A, t to the minus 1/2, in case you're wondering what that looks like for an entry, UV. So this is 0 if U and V are not adjacent. And can anyone see what it would be if U and V are adjacent? Okay, we can't. There's a 1 on the numerator.
Square root degree U.
Yep, square root, degree U, degree V. That's what it looks like. Which is why when you come to this from a combinatorial perspective, you're like, this is not counting. Square roots are wrong. We want whole numbers. Whole numbers. We want it to be holy, but that's unfortunately it is what it is. Okay, so that shows us why our eigenvalues are real. We know that if we're connected and not bipartite, we have one eigenvalue of 1. All the rest are less than 1. If we are bipartite, by the way, we have one eigenvalue of 1 and one eigenvalue of -1. And you can either say prone Frobenius, or you could just say, well, there's a couple ways to argue it, so we'll just say prone Frobenius. Why not? If we have a sledgehammer laying around, we can go ahead and use it to open up a peanut shell. If it works, it works, right? Okay, so I wanted to get back to an earlier comment. We won't have time to fully develop it, but I want to talk about, how do we think about random walk? So we talked about the idea of you have a graph, you start someplace, and then you move, and then randomly, and you move around, Okay, but where are you after 20 steps? And the answer is, it depends, right? What series of choices did you make? There are many things that could have happened. So it's not to say like, I take a random walk, so after 20 steps, I'm here. What we want to say is, you take a random walk, after 20 steps, here's the likelihood where I am. So we need to talk a bit about probability distributions. And so when we talk about random walks, we really start by talking about probability distributions.
So because P is similar to a symmetric matrix, P is diagonalizable, right? But
sure, we'll go with that.
I think that's it's no longer diagonalizable by orthogonal matrix, so you can't necessarily choose your eigenvectors to be orthogonal anymore, right?
I think you can probably. There are certain things about left versus right eigenvectors that you can say, but you have to be careful because left eigenvectors and right eigenvectors for P will be different, whereas for this normalized adjacency, they'll be the same. And in fact, that's going to be an important difference when we get to what's called the stationary distribution, which based on our current speed, we will not talk about today. But at the very least, we should define a probability distribution and say, how do we think about it? Okay, so what are some important facts about a probability distribution? Well, in some sense, there's sort of two important things that should be true about a probability distribution.
Your possible states to 0 to 1.
Okay, so one of the things you just said, 0, 1. So all probabilities have to be greater than or equal to 0. So I can't have a negative probability of being at a certain place. There's like a negative 1/4 chance I'm at that vertex. That doesn't make any sense. So I can have a 0% chance of being at a vertex. That's certainly true, but I can't have a negative % chance. And there's another thing that's sort of implicit, because you talked about the one. So what's the one here? The one. So the probabilities have to be non-negative and?
Oh, they have to sum
Yeah. The sum of the probabilities
somewhere.
have to sum to 1. Now we're doing sums because we're discrete. If we were somehow being very complicated and continuous, we'd have to do integrals, but well, sums are like the integrals of finite things because they are. That's, yeah, true story. So in terms of practical things, if we're thinking of a probability distribution matrix for P, well, it's an assignment to the vertices. The probability that you're at a certain vertex. So we have a vector. So we're going to associate our probability distributions will be associated with vectors. Now the question, left or right?
One leads to certain death.
Funny how they set it up as left.
Really? Ah, good.
And that
Yes.
bothers me so much.
Well, because we're so used to doing it with the right. So the key here is these will be row vectors. So P1, P2, Pn. Well, I mean, you can always write it as a column vector and put transpose, but that feels really inefficient. So, right, so the question is, of course, how do we use these? So let's call our probability distribution F. So what happens after we take one step? And the key thing is to understand that after one step, so take one step in the random walk. So we start with the current probability distribution. We take one more step. What's the resulting probability distribution? And the answer is F times P. And I think this is a good place for us to stop.